I'm going to start with a discussion of variable importance. Okay, so how important is a variable? This is a fundamental question. It haunts data science, statistics, and any field that uses causal inference, like the social sciences, economics, political science, and sociology. The problem is that I don't actually know what this question actually means, and I don't think most people do either. So some people say, how important is that variable? But they implicitly mean how important is that variable to a specific model. So they might want to know that their model F1 depends heavily on some variable V. The problem with this is that it doesn't say very much about variable importance in general. Like, what if there's another model that's equally good in every measurable way to F1, called F2, and it doesn't depend heavily on variable V. Okay? So, and this could totally happen because variables are correlated with each other. So you can definitely have pairs of models that are equally good, and one depends heavily on some variable and the other one doesn't. Okay, so you can investigate. Okay, so knowing how important a variable is to one model doesn't tell you how important it is in general. And you can investigate variable importance for one model, but that's just one model, and it doesn't tell you about how generally important a variable is. Okay, so let's try again to define variable importance. So now I want to know, will I get the same accuracy with and without the variable? Okay, so in other words, I'm supposed to run my algorithm, I get a model, and then I remove the variable, and then rerun the algorithm with all the rest of the variables still in there, and I get another model. And then I determine whether I've lost any accuracy by removing variable v. Okay? So because you see, if I lost any accuracy, then maybe that variable was important after all, because when I removed it, my loss went up. Okay, so the problem with this is that knowing how important a variable is to two models does not tell you how important it is in general. Because you could have run your algorithm and gotten a model that didn't depend on variable v in the first place, and then when you took variable v out and reran the algorithm, it still didn't, that F2 is essentially the same as F1, and it doesn't depend on variable v anyway. But of course, it could turn out that there exists a third model, F3, that depends heavily on v, that's equally good to F1 and F2 in every measurable way. Okay, and of course, this could happen because, again, it depends on the correlations between the variables. Okay, so, but this actually does say something, because this is asking how important a variable is for an algorithm on a data set. It's not asking how important a variable is to a model. It's asking how important a variable is to an algorithm on a specific data set. And it tells you, whether v is necessary for good performance. Because you see, if when you ran the algorithm twice and got different accuracies, then actually maybe variable v was needed to get that extra level of accuracy. Okay, so this analysis would show that we do or we don't need variable v in order to perform well. So we're getting closer. So third try, maybe third time's a charm. So I want to ask, how important is a variable to any good model? Because, if none of the variables, if none of the good models depend on the variable, then the variable's not important. And if all of the good models depend on the variable, then the variable is important. And to me, this is a kind of a more meaningful notion of variable importance. And this actually affects the study of proprietary models because, if you have a proprietary model, you can determine whether it performs well because you can look at its output. But you don't know what variables the proprietary model depends on. So if every good model depends on variable v, well, maybe the proprietary model also depends on that variable v. Okay, so in practice, when we're computing this, we're going to, when I say any good model, I'm going to restrict to studying a flexible but restricted function class so that we can compute but not overfit. Because when I say any good model, it could be like any good overfitted model, but I don't want to overfit. So I'll describe this more in a minute. Okay, so I'd like to define the Rashomon set as the set of good models. So I'll define the set of models such that the models have low loss on the data. Okay, so when I say loss, it could be mean squared error, but it could also be classification error or whatever loss function you want. Okay, so the Rashomon set is the set of good models. And then I'm going to define what I mean by commuting a variable. So X is, you got your data set. The rows are observations. The columns are features. And so when I say I'm going to permute a variable, what I mean is that I'll take the column that represents that variable and reorder it. Okay, so if the variable is age, when I reorder it, I mean I scramble it, I really mess it up, just completely mess it up. So it's so here I'll do it there. So there, I messed it up. So if that variable is age, that's like me assigning your age to her and her age to her and her age to her and so on and so forth. Okay, so I'm kind of killing the joint distribution of that variable with the other variables when I do this. So I call this X scramble because I scrambled that variable up. Okay, and then what I'm going to do is compare the loss of the original data, the model on the original data, to the loss on the scrambled data. Okay, and I'm going to call that the model reliance of F, my model F, on my variable V. Okay, so in other words, if the model reliance is 2, then the loss doubles if we permute that variable V. Okay, so V was actually important to F because when I scrambled it, my loss increased by a factor of 2. And if the model reliance is 1, then the model F doesn't depend on the variable V at all because when I scrambled V, nothing changed. Okay, so I've got these two definitions. I have the set of good models, which is the Rashomon set, and the model reliance, which determines how important a variable V is to a model. This model reliance is, by the way, very similar to what the variable importance for random forest. Okay, so now I want to ask this question: how important is a variable to any good model? And what I'm going to do is technically define that to mean what is the model reliance of functions in the Rashomon set. So again, model reliance is variable importance, and then Rashomon set is all of the good models. So I'm investigating, what is the range of variable importance for the set of good models. Okay, so I want you to hold that thought, and I'm going to get back to this, but I want to tell you about criminal justice for a little while. I'm going to start the talk all over again and talk about criminal justice this time. Okay, so this is a paper. This is a shot of our archive page for this paper that we put it on archive in March 2015. And the authors are Jiming Zhang, who was my undergraduate, and she was working with Burke Houston, who was my PhD student at the time. And so we wrote this paper on interpretable classification models for recidivism prediction. So Burke's PhD thesis is on interpretable machine learning models, which is my area of expertise. And so we had a big publicly available data set, and we were examining whether you needed black boxes to predict whether someone would commit a crime in the future, or whether someone will be arrested for a crime, different than whether they committed it, but still predicting future arrest, and for various different types of crimes. So property crimes, drug crimes, violent crimes, stuff like that. And we had a couple of conclusions in our paper, the main one being that most machine learning methods had very similar performance across the different recidivism prediction problems. So essentially, it didn't matter which machine learning method you used. They all performed the same. And that included our new interpretable modeling methods. And these methods were producing predictive models that were so tiny that it looked like a human could have written them down without even looking at data. I mean, they were like, they could fit in this box on the slide. And another conclusion that was not one of our main conclusions, but was in the paper, was that race, the variable race, was not useful for predicting recidivism, but it was correlated with criminal history. And it was also correlated with age. So when you put in age and criminal history and add race, you're not really getting extra accuracy out of that. Okay, so that was in 2015. a year later, there was this article that kind of made headlines by the ProPublica group. And what they were doing was they were accusing a proprietary model that's used throughout the justice system of being racially biased. Now, the model that they were accusing is called COMPAS. I think it's like Correctional Offender Management Profile, something. And that model is proprietary. It has 130 plus factors in it. This is not necessarily the simplest model in the world. The company, NorthPoint, that makes COMPAS, they make money off of using that model in the justice system. Now, this article it launched an entire literature on algorithmic fairness in black box models. But like when I read this, the whole premise just didn't make sense to me. Like the whole premise of using COMPAS in the justice system, like a super complicated proprietary model to predict recidivism, it didn't make any sense to me. And the conclusions of ProPublica's article didn't make any sense to me. Like I had a completely different perspective on this than both the justice system and ProPublica. It was like I was living in an alternative universe and what's really going on here. So here's what I saw. The world was saying, okay, we need a black box because, COMPAS is used widely in the justice system, and they're saying we must need a black box because otherwise, why would we pay this company and the taxpayer has to pay for all these giant surveys to be collected, and we must need this. It must be important. And our paper said interpretable models were just as good, so you don't need black boxes. Oh dear. And then ProPublica says COMPAS depends on race, even after conditioning on age and criminal history. That's what they said. And then our paper said, well, there's no need to use race after conditioning on age and criminal history, so any reasonable model wouldn't do that. Okay, so then there is one big difference between the world and us, which is that there's a huge amount of money involved in this, and also an incentive to, there are people who have an incentive to make more money at the expense of the quality of the justice system. And they also have a lot of data, right? My taxpayer money is paying NorthPoint for the collection of that data for COMPAS in the justice system, but I can't get that data. It's owned by NorthPoint. So we didn't even have a grant to work on this. We were just doing it. Okay, so the one great thing about the ProPublica article was that they made everything reproducible. They actually provided a whole bunch of COMPAS scores. So provided a whole bunch of outputs of this black box model that we could use to actually do some analysis to figure out what's going on. And that data was from Broward County, Florida. And so we could just try to figure out, what is the discrepancy? So we said, fine. So my lab, again, we work on interpretable machine learning. So we said, okay, let's take the COMPAS data that they gave us and let us compare it with our latest machine learning model for interpretable machine learning. That happened to be a decision tree model. It's called Corals. So Corals is a competitor for CART, which is classification and regression trees. Like CART is like a wheelbarrow, and this is like a sports car in comparison. Like this thing, it doesn't do greedy splitting and pruning. It finds globally optimal decision trees. It uses computer systems techniques to work very, very quickly. It has specialized data structures to keep track of symmetries and intermediate computations. It has its own big vector library. It has a whole bunch of theorems to bound parts of the search space so that we never need to search there. It's like, a really powerful modeling tool. And when we launched, and COMPAS, by the way, has this very fancy name over here, whereas ours was called Certifiably Optimal Rule Lists. Okay. So anyway, Corals found this model in all 10, essentially the same model in all 10 phones. I mean, sometimes you see small variations, but mostly the models look like this. If you can't see at the back, it just says if age is between 19 to 20 and you're male, predict the rest. As it turned out, you could take out male and it wouldn't really change the accuracy very much. Okay, so if you're young and you're male, predict that you'll be arrested within 2 years of this COMPAS score, of the COMPAS score being computed for you. Else, if you're between ages 21 and 22 and you have 2 to 3 prior offenses, predict arrest. Else, if you have at least 3 prior offenses, predict arrest in the next 2 years. Otherwise, predict no arrest. Okay, so this is not a model that a person wrote down by hand. This is a model that came out of this algorithm. It's a interpretable machine learning model. Okay, and the interesting thing about this model is that it has almost exactly the same accuracy as COMPAS for predicting recidivism, and it has the same true positive rate, false positive rate, true negative rate, and false negative rate as COMPAS for both blacks and whites. So we said, okay. And there's no explicit dependence on race here, right? The algorithm could have used race if it wanted to, because race was in the list of variables, but it chose not to use that. I mean, certainly race is sort of embedded in here because it's correlated with age and criminal history, right? Okay, so the nice thing about this is that it's completely transparent. Okay, not 137 factors at all. Okay, so I'm still looking at this. I'm still looking at this comparison, and I'm still on this side. Okay, so let's investigate the race question. So ProPublica says that COMPAS is racially biased, and after you include age and criminal history, there's still some dependence on race. So we say any decent model wouldn't use it, but that doesn't mean COMPAS doesn't depend on race. Okay, so why did ProPublica think that COMPAS depends on race? Okay, so what ProPublica actually did was they created a linear model to approximate COMPAS, and they created coefficients for age, criminal history, and race, and they found that those were all positive. So they're saying, okay, when we take age and criminal history into account, there's still dependence on race. Okay, does that mean that race is an important variable for COMPAS? Well, as we know, we could discover a model F1 where variable V is important, but there could easily be a model F2 that is just as good as model F1, but that doesn't depend on variable V. So there's no way that ProPublica should have concluded from this analysis that COMPAS depends on race, right? Criminologists also thought that this analysis was ridiculous, but that begs the question of what does COMPAS actually do? So COMPAS is proprietary. It uses 137 factors, many of which we don't have because the data are not public. It's survey data. And COMPAS's manual, if you read the manual, it claims that there's a linear dependence on age. But that's not really what the data says. So we have 2 conjectures. We can't prove these conjectures because we don't have all the data. But our conjectures are that the 2 COMPAS scores actually depend in a kind of approximately polynomial way on age. So there are 2 COMPAS scores. There's a general recidivism score for predicting arrest, and then there's a violence score, which predicts violence arrest. So there are these two scores, and we think the first one is approximately quadratic, and we think the second one is approximately quartic. Like I said, we can't prove these, but we have a lot of evidence to suggest that this is true. So this is not a linear dependence. That's the important part here. Okay, so it's a little complicated. There's a lot of reasons that go into the evidence for this, but I think the easiest way to show you the evidence is to show you a plot of COMPAS, the COMPAS score versus age for all the individuals in Broward County, Florida. Okay, so this is age at the COMPAS screening date. So this is when your COMPAS score got computed. And this is the COMPAS score itself. And you'll see that there's, the COMPAS scores are all over the place for different ages, but there's a lower bound here. And the lower bound consists mainly of individuals who have no criminal history. And for those people, if you look at this, this is actually does not look linear. This curve is not linear. It's actually somewhat curved, okay? So we have a lot of kind of evidence to believe that this is actually the contribution of age to compass. And there are actually multiple people on these lower bounds that actually achieve the same raw score, compass raw score. Okay, and then this is for the violence score. And again, it really doesn't look, there's clearly a nonlinear dependence somehow on age going on there. Okay, and there are those two polynomials that I showed you earlier, the quadratic and the quartic. Okay, so a lot more details about this analysis are in the paper and why we think this is actually the age contribution to compass. Okay, so ProPublica's analysis definitely isn't right, but Compass's manual also seems wrong. So does compass depend on race? You know, conditioned on age and criminal history, which are, again, correlated with race. So we said, okay, our first try is, let's just subtract off what we think is the contribution of age to compass. So we'll just subtract off the age bit, and then we're going to run machine learning methods with and without race to see if they need race to predict compass well. Okay? So we did that, and I know it's hard to read these tables on the screen, but let me tell you what this is. The top part is the general score, the bottom part is the violence score, and these are lots of different machine learning methods, and then with race and without race. And what you're supposed to see from these tables are that these pairs of numbers are almost identical. I mean, they're very, very similar to each other. So in other words, running the algorithms with race and without race, we just really didn't see very much difference between the numbers. So far, I'm not seeing any indications that compass is necessarily depending on race other than through age and criminal history, which are the factors that we have in our machine learning models. Okay. So, unfortunately, this isn't the whole story, because as you know, knowing how important a variable is to two models does not tell you how important it is in general. So let's try again. Now let's try looking at a flexible class of models so that hopefully at least one of these models is fairly similar to its variable importance to compass. And we're going to try to find the range of model reliance of functions in the Rashomon set. Okay? So we'll find out, essentially, you know, if we try really hard to get our approximation of compass to depend on race, how much can we do it? Okay, so I just want to remind you of these definitions. Again, the Rashomon set is the set of good models, so low-loss models. And the model reliance is the ratio of the scrambled loss to the non-scrambled loss, so it's variable importance measure for a function and a variable. Okay, and so we're trying to look at the range of variable importance, the model reliance, all the functions in the Rashomon set. So it's going to be a range. And again, if the model reliance is 1, it means that the function doesn't depend on the variable. Okay, so we chose a pretty flexible model class. We used our variables, which are age, criminal history, gender, and race as regressors. And there's some details about the flexible model class here. It was kernel regression with a variable size kernel. And then we decided to calculate the model reliance on race and gender. So Aaron Fisher, who did this analysis, lumped together race and gender. Now, because it's now the model reliance for all the functions in a class, we're now going to call it model class reliance, so that you get the whole model reliance for all the functions in the class. Okay. So here's what we get. So it turns out that there is a model, at least one model, that has low error that depends on race and gender. In fact, if you took that model and scrambled race and gender, then the loss could go up by a factor of 0.5. But there are also models that don't depend on either race or gender and just predict as well as any good model. And this analysis we did before we figured out the age polynomial. So if we subtracted out the age polynomial and redid it, I suspect that this would go like all the way down, to be honest. So you can sort of force a dependence on race if you wanted to by pushing all of the signal of all the other variables into race, but you just can't force that error to go up a huge amount relative to what it already is. Whereas if you did, and this is a 95% bootstrap confidence interval on that. But if you did the same analysis with age and criminal history, then the error goes up by a factor of at least 1.77 all the way up to like 3.5, over 3.5. So age and criminal history are by far the more important variables here. Okay, so this analysis, of course, assumes that our flexible class is flexible enough to get close to compass so that we can have a similar model reliance from our variable and compass. And that assumption is that's up for debate, but that's what this analysis depends on. Okay, and there's the bootstrap confidence intervals on that. Okay, so great. So this logic here still makes sense to me. But compass doesn't depend on only age and criminal history, right? It depends on a whole bunch of other factors. If it doesn't depend on a whole bunch of other factors that are correlated with race, what the heck does it depend on? Well, I don't know, but what I can tell you is that I didn't yet discuss the most, possibly the biggest reason not to use compass. Okay, so there's a serious disadvantage to using complicated proprietary models that I haven't mentioned yet, which is that, you have 137 factors entered for each individual on the compass score by hand, right, for each survey. And if you have a 1% error rate on this data entry task, then there's a 75% chance of at least one typo on each survey. So what that means is that you have cases like the case of Glenn Rodriguez that was in the New York Times, where he figured out that his compass score was calculated incorrectly, and he was denied parole based on that compass score. He was in prison since he was like a teenager, and he finally comes up for parole like 17 years later, and his parole gets denied, and he's like, what? And then he compared his compass survey with someone else's, and found that there was a typo in his criminal history. And he was denied parole, and the parole hearing was over, so there's nothing he could do about it. So if compass is being used to make these kind of high impact decisions that really impact people's lives, we have to be careful about this issue. So you have this huge mess where the taxpayer dollars pay someone to sit there and collect all this very private survey information, like whether your mother was ever arrested or other things like that, making typo after typo that's really difficult to check, and the information goes only to this one company, and that leads to what? Bad decisions. Okay, so we were looking at the Florida data to try to figure out how often these typos might happen, and we found some strange inconsistencies in the data. So what I'm showing you here is part of a table that we have where it's people with compass violence score 1. So this is the lowest compass violence score. Compass scores range from 1 to 10. So 1 means no risk. That's low risk, very, very low risk. And then this is the number of prior crimes these people had, and it ranges from like 4 to 40 on just this table here. And then here's a list of some of the past crimes that they committed. So for example, this person here has 40 past crimes, including battery on a law enforcement officer, attempted robbery with a deadly weapon, and so on and so forth. So he has a compass score of 1. Now, the interesting thing about these data is that this is part of the ProPublica data set. So these are actual people's names. Criminal history data is it's like publicly available data. It's like the phone book, okay? Whereas how this score is calculated for that person is private. So there's this very strange, that's why I put the names up, to show this weird inconsistency in this thing. Anyway, so like this guy, for instance, here are crimes that he committed after his compass score was computed. Okay, that's part of a much longer table where, I'll zoom into a different part of that table, where you have other people with very low compass scores, again with very long criminal histories that indicate, carrying a concealed firearm, battery on a law enforcement officer, home invasion, robbery, all kinds of stuff like that, Okay, so the current state of affairs is that we're relying right now on human judges. Human judges are biased black boxes. Even when humans explain their reasoning processes, it still may not be the true reasons that they made their decisions. Compass is an alternative. It's a black box. It has possibly incorrect documentation on whether it depends linearly on certain variables, which makes it very difficult to check whether it's biased in any way to any group. It's not reliably computed because of potential typos with 137 factors. And there are financial incentives to keep it there because of the way the justice system is set up. Right now, so I don't know whether Compass is fair. I'm not the right person to judge that, but I can say that it has a kind of procedural unfairness where typos can end up making huge life-changing decisions for people, and I don't think that's fair at all. Okay, California is moving toward a no-cash bail system, possibly using Compass. There's a lot of arguing about that. This is, I think, one of the latest articles on that topic with the argument going on. And they're not agreeing on whether to do this. Now, also, ProPublica's seriously flawed analysis is still highly cited and respected. Almost every article I've read on fairness lately has cited that article. Now, academic interest in fairness is huge. That stemmed somewhat from the ProPublica article. The interest in explainability of black boxes is huge. However, there is still very little interest or expertise in designing models that are actually interpretable so that we can replace the black boxes with transparent models. Right? If we use transparent machine learning models, we could potentially fix some of this stuff, both the black boxes and the bias. And this would provide technical solutions to these problems, right? Machine learning methods that provide transparent models, but people aren't paying attention. Okay, so what I'm essentially suggesting to do is replace something like this with something more similar to something like that. Okay, and these are my wonderful collaborators on all of these projects. So thank you very much.